Good day, viewers. My name is Agali Belinda Chizob. I'm taking you on the subject chemistry and the topic solubility, how to determine solubility, and then uses of solubility curve. By the end of the lesson, students should be able to define solubility, calculate solubilities of different compounds, list factors affecting solubility of salts and solvents, describe a solubility curve, and list the uses of a solubility curve. The solubility of a solid in a liquid is the concentration of a saturated solution, meaning the amount of the solid that dissolves in 1 dm cube of the solution at a given temperature. It can be expressed in moles per dm cube. It is also the maximum mass in grams of the solid that dissolves in 1,000 grams of the solvent at a given temperature. Solubility can also be regarded as concentration, meaning the amount in a solution or the amount in a solvent. Hence, it can be expressed in moles per dm cube, or gram per dm cube, or gram per 100 gram, or gram per 1,000 gram of the solvent. Solubilities of solid increase as temperature increases, except for solids such as calcium hydroxide, calcium tetraoxosulfate 6, whose solubilities decrease as the temperature increases. Imagine when you want to dissolve Milo beverage inside cold water. Some of it will be hanging on top of the water as though it's a suspension, but when you add it inside cold water, it will dissolve immediately, meaning that solubilities increase as temperature increases. Pressure will have no effect on the solubility of solids, while the solubilities of gases decreases as temperature increases. Increase in pressure will increase the solubility of gases. What I say in essence that temperature affects the solubility of solids, while pressure affects the solubility of gases. Determination of solubility using potassium nitrate at 30 degrees C. The saturated solution of the salt is first prepared by the following steps. Put 100 cm cube of distilled water in a beaker. Add the salt little by little and warm on a Bunsen burner with stirring. Continue the addition of salt with stirring and keeping the beaker warm at about 50 degrees C until the salt can no longer dissolve. Allow the saturated solution to cool to 30 degrees C. This is the saturated solution of the salt at 30 degrees C. It will be noticed that as the hot saturated solution cools, the excess solid in the solution separates out to give a saturated solution at a lower temperature. Weigh accurately a clean, dry evaporating dish. Let us say the weight of the evaporating dish is S gram. Rinse a 25 cm cube pipette with the saturated solution in order to warm it. Prepare 25 cm cube of the saturated solution at 30 degrees C as quickly as possible without pipetting any undissolved solid into the evaporating dish and reweigh. Let us say that the weight of the evaporating dish plus 25 cm cube is Y gram. Place the dish on a steam bath and evaporate to dryness. Allow to cool in a desiccator and then reweigh. Repeat the process of heating and cooling until a constant mass is obtained. Let us use the following hypothetical results to demonstrate how to calculate the solubility of a salt. Data required. Mass of evaporating dish, which we have labeled S, let us say it is 15.20 gram. Mass of evaporating dish plus water, which we labeled Y, let us say is 40.70 gram. 25 cm cube of saturated solution. Mass of anhydrous salt, that is when you have heated, allowed to dry and cooled, let us say is 20.70. Then mass of anhydrous salt will be W minus X, which is equal to 20.70 minus 15.20 to give us 5.50 gram. That is 25 cm cube of saturated solution contains 5.50 gram. It means that 1000 cm cube will contain 5.50 times 1000 divided by 25 to give us 220 grams of the salt. Since amount in moles is equal to mass over molar mass, and molar mass of potassium nitrate is 39 for potassium, 14 for nitrogen, and 16 times 3 for oxygen to give us 101. It means that solubility in mole per dm cube will be 220 grams, which is in 1000 cm cube or 1 dm cube, divided by the molar mass of the salt to give us 2.18 mole per dm cube. Solubility in 100 grams of water. Mass of water used is Y minus W, which is 40.70 minus 20.70 to give us 20.000 grams. Mass of salt used is W minus S, which will give us 5.50. Since 20.0 grams of water at 30 degrees C saturated 5.50 grams of salt, therefore 100 grams of water at 30 degrees C will saturate 5.50 times 100 over 20 to give us 27.5 grams of salt. Hence, the solubility of salt at 30 degrees C is 27.5 grams per 100 grams of water. The solubility of a salt, such as anhydrous sodium carbonate, potassium carbonate, sodium hydrogen carbonate, or potassium hydrogen carbonate, can be determined by titration. This is achieved by preparing a saturated solution of the salts at room temperature and then diluting it to a known volume. Dilution may not be necessary if the saturated solution is not of high concentration. The diluted solution is then titrated against a standard solution of an acid if the aqueous solution of the salt is alkaline, and vice versa. What we mean is that if the salt you are trying to determine its solubility is acidic, that means you should titrate it against a standard solution of an alkali. For example, A contains 0.101 mole per dm cube HCl. B is obtained by diluting 25.0 cm cube of a saturated solution of anhydrous sodium carbonate at 25 degrees C to 1000 cm cube with distilled water. 25.0 cm cube portions of B require an average of 24.35 cm cube of A for complete neutralization using methyl orange as indicator. From the above data, calculate A, concentration of solution B in mole per dm cube, B, solubility of sodium carbonate at 25 degrees C in mole per dm cube, and mass of sodium carbonate obtained when 1 dm cube of saturated solution was evaporated to dryness. Equation of the reaction: 2HCl plus sodium carbonate to give you 2 sodium chloride plus water plus CO2. This is the atomic masses of sodium, oxygen, and carbon. Solution: since we want to find the concentration of B, we are going to use this concentration of A multiplied by volume of acid divided by concentration of B multiplied by volume of base equals number of moles of acid divided by number of moles of base. Where Ca is concentration of A, remember that our A is 0.101 mole per dm cube of HCl. Our Cb is what we are looking for. Our Va is the volume of acid used, and Vb is the volume of base, while Na is number of moles of A, and Mb is number of moles of B. We have substituted it and make Cb subject of formula to have 0.101 times 24.35 times 1. 1 is the number of moles of acid. Number of moles of base. Y2 is the number of moles of acid. And if you point the calculator where you have 0.0492 mole per dm cube, which would be the concentration of base or concentration of sodium carbonate. Two methods can be used. The first one is proportion method. Since 25.0 cm cube of B is found to obtain 0.0492 mole per dm cube, it means that 1000 cm cube should contain 0.0492 multiplied by 1000 divided by 25 to give us 1.97 mole per dm cube. II. We can also use formula method or dilution principle. Dilution principle is C1V1 equal to C2V2, where C1 is the concentration we are looking for, V1 is 25 cm cube, C2 is 0.0492, while V2 is 1000 cm cube. If you make C1 such a formula, you're going to have 0.0492 multiplied by 1000 divided by 25 to give us 1.97 mole per dm cube. Then to find C, that is the mass obtained when you evaporate the solution, we have since number of moles is equal to concentration in mole per dm cube times volume in dm cube, to give us 1.97 times 1.9 equals to 1.97 moles. And mass in grams is moles multiplied by molar mass, to give us 1.97 multiplied by the molar mass of sodium carbonate, to give us 1.97 times 106, which is equal to 208.8 grams or 209 grams. Another example is this. Calculate the solubility of sodium carbonate at 25 degrees C. If 30 cm cube of this saturated solution at this temperature, or at that temperature, gave you 1.80 grams of the anhydrous salt. Remember that 30 cm cube contains 1.80 grams. That means that 1000 cm cube will contain 60 grams. And since we know that number of moles is equal to mass over molar mass, we can use 60 divided by the molar mass to give us 0.566 moles or moles per dm cube. Example 4. In an experiment to determine the solubility of a given salt, Y, the following data were provided. Mass of the empty dish is 7.16 grams. Mass of dish plus saturated solution of salt, Y, is equal to 17.85 grams. Mass of dish plus salt, Y, is equal to 9.30 grams, while the temperature of the solution is equal to 25 degrees C. Molar mass of the salt, Y, is 100. Density of the solution, Y, is 1.00 gram per cm cube. Calculate the solubility of Y in I, gram per dm cube, II, mole per dm cube of solution. Solution to our problem. Our mass of salt will be mass of dish plus salt, Y, minus mass of dry empty dish, which is equal to 9.30 minus 7.16, to give us 2.14 grams. Mass of solution is equal to mass of dish plus saturated solution of Y minus mass of dry empty dish, to give us 17.35 minus 7.16, to give us 10.69 grams. Since 10.69 grams or 10.69 cm cube contains 214 grams, therefore 1000 cm cube will contain 2.14, multiplied by 1000 divided by 10.69 to give us 200 grams per dm cube. And since number of moles is equal to mass over molar mass, we can use 200, which are found in gram per dm cube, divided by 100, which is the molar mass, to give us 2.00 mole per dm cube. Example 5. If 50 cm cube of a saturated solution of potassium nitrate at 40 degrees C contains 5.05 grams of the salt, what is the solubility of the salt at that temperature? The molar mass of potassium nitrate is 101. Yes, 101. So it simply means that by logic, since 50 cm cube will contain 5.05 grams, then 1000 cm cube will contain 5.05 times 1000 divided by 50, which is equal to 101 grams. And we know that number of moles is equal to mass over molar mass. Since we have 101 grams per 1000 cm cube of solvent, and the molar mass is also 101, therefore our solubility is 1.00 mole per dm cube of the solution. Example 6. 30 grams of sodium chloride saturates 15 grams of water at 10 degrees C. Calculate the solubility of sodium chloride at that temperature in grams per 100 grams of solvent. At 10 degrees C, 15 grams was saturated by 30 grams of sodium chloride solid. Therefore, 1 gram of water will be saturated by 30 divided by 15. Therefore, 100 gram of solvent will be saturated by 30 divided by 15 multiplied by 100 to give you 200 gram per 100 gram of solvent. Example 7. At 30 degrees C, the solubility of sodium chloride is 58 gram per 100 gram of water. Calculate the mass of sodium chloride that will be left after evaporating 20 gram of this solution to dryness. Solution. At 30 degrees C, the mass of the saturated solution of sodium chloride is 158 gram. That is 100 gram of water plus 58 gram of the sodium chloride. If 158 gram of the solution of evaporation gave us 58 gram of sodium chloride, then 1 gram of solution will give 58 divided by 158. Therefore, 20 grams of saturated solution of sodium chloride on evaporation will give 58 divided by 158 times 20 over 1 to give us 7.34 grams of sodium chloride. Determination of solubility using solubility products, which is KSP. When the equilibrium law is applied, remember that equilibrium simply means having the same amount or the same amount in concentration, It can be stated that a solution is saturated when undissolved particles are in equilibrium with the solution. Since solid plus water gives us solution, or solids plus water is equal to solution, solubility equilibria are limited to ionic compounds whose solubilities in water are so small and they can be described as being insoluble or sparingly soluble. Examples include silver chloride, lead sulfate, barium sulfate, silver bromide, zinc sulfate, lead sulfate, and copper sulfate. Like any equilibrium system, the equilibrium constant K for a sparingly soluble salt can be obtained from the equilibrium concentrations. For instance, consider the solubility of silver chloride in water. It will dissolve to give us silver ion and chloride ion. At equilibrium, the equilibrium constant Kc is the concentration of the products divided by the concentration of the reactants. By convention, the concentration of silver chloride, which is in solid form, is equal to that in water, which is equal to 1. Since silver chloride is a solid and water is a pure liquid. Therefore, the equilibrium constant for silver chloride will be equal to concentration of silver ion multiplied by concentration of chloride ion to give us KSP. The new equilibrium constant KSP is known as the solubility product. The solubility products of some salts are shown in the table below at 25 degrees C. These are the salts. Why is this that they are solubility product constants at 25 degrees C? Let us take an example of how to calculate solubility from the solubility product. The solubility product of silver chloride is 1.70 times 10 raised to the power minus 10 at 298 Kelvin. Calculate its solubility. Solution. When silver chloride is dissolved in water, 1 mole of silver ion and 1 mole of chloride ion are formed, that is at equilibrium. Therefore, KSP is the concentration of silver ion multiplied by that of chloride ion to give us 1.70 times 10 raised to the power minus 10. Let us say that the concentration of silver chloride is X and that of chloride ion is also X. So X times X is equal to 1.70 times 10 raised to the power minus 10. X times S is already X squared to be equal to 1.70 times 10 raised to the power minus 10. Therefore, X will be the square root of 1.70 times 10 raised to the power minus 10, which is equal to 1.30 times 10 raised to the power minus 5. Let us take another example. A saturated solution of lead 2 chloride contains 4.73 grams per dm cube at 25 degrees C. Calculate the solubility product of lead chloride at this temperature. They have given us the molar mass of lead and that of chloride ion. Solution. Since solubility in moles per dm cube is equal to solubility in gram per dm cube divided by molar mass, that means that 4.73 gram per dm cube can be divided by 207 plus 71. Remember that the formula for lead chloride is PbCl2, so that 5.5 will be multiplied by 2 to give us 71 to get 0.0170 mole per dm cube. At equilibrium, each mole of lead ion will form 2 moles of chloride ion. Since Ksp is equal to lead-2 ion, concentration of lead-2 ion multiplied by concentration of chloride ion squared. We know that 0.0170 in brackets multiplied by 2, 0.170 is getting from here, multiplied by 2 times 0.0170 squared is equal to 1.96 times 10 raised to the power minus 5. That is the Ksp for lead chloride at this temperature. Factors affecting solubility. Factors that affect the solubility of solids in liquids include the following. One is the nature of the solids. Ionic compounds are soluble than covalent compounds in polar solvents like water, while covalent compounds are more soluble than ionic compounds in non-polar solvents like petrol. For instance, sodium chloride is more soluble than sugar in water at room temperature. What we are saying in essence is that like will dissolve like. Just like the saying goes that birds of the same feather flock together, meaning that ionic compounds will dissolve ionic compounds, and covalent compounds will also dissolve covalent compounds. Nature of the solvents. Generally, ionic compounds are more soluble in polar solvents like water than in non-polar solvents like petrol. An increase in the polarity of the solvent increases the solubility of the ionic compounds. For example, sodium chloride is more soluble in water than in ethanol. This is because water is more polar than ethanol. Common ion effect. The solubility of an ionic compound in water is not affected by the presence of another compound already in solution, except if both compounds have the same cations or anions. I will explain. For instance, the solubility of sodium chloride in water is the same as its solubility in dilute sugar solution or in dilute H2SO4. This is because there is no cation or anion common to sodium chloride, which is the solute, sugar, which is the solvent, and also H2SO4, which is also the solvent. The solubility of sodium chloride in water is much higher in water than its solubility in HCl or aqueous sodium nitrate. This is because in sodium chloride and sodium nitrate, sodium ion is common, and then in sodium chloride and HCl, chloride ion is common. The decrease in the solubility is due to a phenomenon known as common ion effect. Here, sodium chloride is having a common ion between sodium nitrate, while sodium chloride and HCl having a common ion between sodium chloride and the HCl. So the common ion between the two compounds, that is the solute and the solvent, will decrease the solubility. Solubility curve. The solubility curve of a salt represents the variation of its solubility with temperature. It is obtained by determining the solubility of the salt at in a particular solvent at various temperatures. Then a graph is plotted with the solubility in mole per dm cube or 100 grams of solvent along the y-axis, while the temperature in degrees Celsius on the x-axis. If the solubility curves of various salts are plotted on the same graph, for instance, in the graph below, you can see that of Ki, that of sodium nitrate, that of potassium nitrate, that of ammonium chloride, out of KCl, out of ammonia, out of SO2 gas, out of potassium triazochlorate 1, and out of sodium chloride. Let us compare these salts on the graph. You can see that sodium chloride at just above 30 degrees Celsius is having a straight line meaning that at any temperature, be it 100 degrees, be it whatever, sodium chloride will do what? Dissolve. Let us take ammonium chloride. At 20 degrees Celsius, we can see that about 40 grams of the solute will dissolve. But at 100 degrees Celsius, up to 70-something gram of the salt will dissolve, meaning that an increase in temperature favors the solubility of ammonium chloride. But let us take ammonia gas. Remember, ammonia is a gas, while ammonium chloride is a solid. And we said at the beginning that temperature affects gaseous solids or solubility of gases. As temperature is being increased, the solubility of gases decreases. We can see that in ammonia here. As the temperature is being increased, the solubility of the salt is decreasing. The same applies to sulfur 4 oxide here. Use of solubility curve. The first use is in order to extract essential chemicals from their sources. Scientists make use of solubility curves to determine the most suitable temperature to be used with a solvent. 2. To determine the amount of solid drugs in a solution of drug mixtures. And lastly, 3. To separate and purify mixtures of solids. Evaluation. The first one is to define solubility. The second one is to calculate solubility given various data. For instance, an evaporating dish weighed 31.18 grams when filled with a saturated solution of copper tetrahydrosulfate 6 solution at 32 degrees C. It weighed 48.9 grams. After evaporation to dryness, the evaporating dish and residue weighed 33.98 grams. Calculate the solubility of copper tetrahydrosulfate 6 crystal solid at 32 degrees C in grams per 100 grams of solvent. You just find a gram of the solvent, find a gram of the weight of the residue at 32 degrees C, and then calculate in gram per 100 grams of solvent. What is a solubility curve? This is just a curve drawn by using the solvents on the y-axis and then the temperature on the x-axis. Give to importance of solubility curve. We mentioned that you can use it to extract essential oils from their sources. We can use it in prescribing drug mixtures, and we can also use it in separating mixtures of solid. This is an example of using titration to calculate solubility. A is a solution containing 10.6 grams per dm³ of H2SO4. B is a saturated solution of sodium hydrogen carbonate at 25 degrees C. In a titration experiment, 25 cm³ of B required an average of 27.30 cm³ of A for complete neutralization using methyl orange as indicator. Calculate the I concentration of A in mole per dm³, I solubility of B at 25 degrees C, and I concentration of B in gram per dm³. For I, simply use mass over molar mass. The mass is 10.6 grams, and then you calculate the molar mass of this to calculate the concentration of A mole per dm³. For this one, we are going to use CAVA over CBVB equal to NA over NB. Our CB is what we got here. CA, is what we will get here. Our CB is what we are calculating here. Our VA is 27.30 cm³, while our VB is 25 cm³. Then we can also find concentration of B in gram per dm³ from this. Remember that this is in mole per dm cube, while this will be in gram per dm cube. Then lastly, calculate the solubility of zinc sulfide in water at 298 Kelvin, given that the solubility product constant of zinc sulfide at 298 Kelvin is 1.6 times 10 raised to the power minus 24. First of all, write the ionic equation to know the number of moles of zinc and number of moles of sulfide. From there, you can get the solubility, since we have been given the solubility product constant. We have come to the end of our lesson, and I believe that after evaluating yourself with the evaluation guide, you can understand how to define solubility, how to calculate solubility using different methods.